So to begin this video off, I have drawn here a compound of butene, as you can see, 1, 2, 3, 4 carbons here. But before we go into what I want to talk about today, I just want to define a basic term here for you guys, which is a term of stereoisomerism. Now, what a stereoisomer is, it is when two organic compounds have have they have the same molecular formula and structural formula, but they have different arrangements of atoms in space. And I'm going to show you what I mean by that by drawing another version of this, which you may have seen before. I'm drawing another version of this right here. Now, I did talk a tiny bit about this in my other video, but in this video I'm explaining it fully. So here we have two organic compounds of butene. You can tell it's an alkene because of this double bond right here. So I'm just going to go ahead and I'm going to redraw this in blue, but right now I'm just going to butene. And we'll redraw this in a different color just so I can highlight the differences here. CH3, H, and H. Now, what causes this? There, you can see there's been a rotation here of one CH3. This can't move this way, but you can see there's been a rotation here of the CH3. Now, what we can see is that these are two obviously different, but both have the same name if we were to cover IUPAC rules. Butene. Now, these are actually two stereoisomers of each other. And what that means is this double bond here restricts the movement of crossing here. It just allows the turning here, which is what causes this isomerism, this form of isomerism between alkanes. Now, there's two naming systems for this, and the first one I'm going to introduce you guys to is something called E/Z isomerism. And I'm not going to pronounce their German names because I know I will butcher them completely. But just know that E is when the highest priority group, so the highest priority groups, I mean the functional groups of the carbons which have the highest molecular relative formula mass, what have you, if they're on opposite sides. So here we obviously have E, butene. We'll just put it in brackets here to make it less confusing. E, butene. And on this side, you could already guess we're going to have C, butene. And that is because both the highest priority groups are on the same side. And this is stereoisomers. Now, there is another type of stereoisomerism, which is called Cis-Trans isomerism. Okay, and this works in a similar way, but altogether differently. And Cis-Trans isomerism is where two substituent on each carbon. So what I mean by substituents is these different groups, these different atoms, these different groups that are connected to this carbon here are substituent groups, and it's when they are the same that cis-trans isomerism occurs. So, for example, here you can see that we have two CH3s here. So they're the same, and they're on the same side, which means this is a cis isomer. But also these hydrogens act as it as well, because say we have, we're going for this again here, but your hydrogen here and hydrogen here. Here you can see these two are different. However, because there are two hydrogens here, we can still call this a trans isomer, and that is because it has two of the same substituent groups, but they're on opposite sides. So this is, I've drawn a C here. This is supposed to be a Z, and Z is obviously same side is the same side, and E, just remember, for opposite side. Now I want to look a little bit deeper at cis-trans here. I want to look a little bit deeper into EZ isomerism here.